Hello, this is Greg Risteman from Olympus. Welcome today, everyone, to this webinar on ensuring code compliance while using the Total Focusing Method, or TFM. In this webinar, you'll learn about the current codes and standards that apply to FMC and TFM and understand the reasons behind these new requirements. Find out what tools are available to make the code compliance easier. Our presenter today is Dali Suizi. Dali joined Olympus in 2019 as a global markets manager. He's an NDT expert in advanced applications and training. He holds a bachelor's degree in engineering and a Master of Science degree in applied science and is a certified UT and phased array UT Level 3. With a broad range of international experience, he has participated in numerous inspection projects in the nuclear, oil and gas, and steel structure industries. This informational webinar has been scheduled for approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. If we're not able to get to your questions during the event, they will be addressed personally either by email or phone after the webinar is done. Everyone who registered for this event will receive a follow-up email with links to the archived presentation, whether you have attended it or not. Now, without further ado, I'd like to turn the presentation over to Dali. Dali, you may take it away.
Thank you, Greg. Hello, everyone, and thank you for connecting and joining us in this webinar. First, I hope that all of you and your families are safe and in good health, wherever you are. This is the fifth and final webinar in our series on FMC TFM, in which we will focus on how to ensure that your TFM inspection is code compliant. Before we begin, let's have a look on today's agenda. So we will start with the current context of TFM use in the NDT industry and its incorporation in codes. Then we will focus on ASME code requirements, scan plan, Amplitude Fidelity, cal blocks, calibration, and the most important factor actually in any technique, the inspection personnel, of course. We will end this webinar with a myths and facts section, and if time allows it, it will be good to have some question and to try to answer on them. Actually, when FMC TFM was introduced to the NDT community a few years ago through conferences and shows and events, it was perceived as a revolutionary technique that would change the game. However, over time, some limitations and challenges came to light, especially for weld inspection applications. One of them is certainly the existence of several wave modes and the difficulty to select the right ones, etc. Therefore, TFM is mostly used as a complementary technique, mainly for flows characterization, and it's mostly used with phase array, of course. On another hand, lack of knowledge, the number of codes including the technique, and the computing capabilities as well, that is related to acquisition rates and TFM processing time, prevented a fast growth and popularity of FMC TFM. But now, being included in some codes, things may change. This leads us to our first section, FMC TFM in codes. And before we start talking about FMC TFM in codes, I think it's good that we review the list of codes that already incorporated phase array, as it could be a sign that they will probably and hopefully add an FMC TFM section in the next few years. So ASME code actually started with having, at the beginning, some code cases talking about phase array and how to do with this technique, and then it comes with an included part of phase array. So now in Article 4 and 5 and Appendix V and P, we have phase array. ISO, the same thing in his many standards. Actually, here I picked up just two, for example, has the phase array included as well. API, in its standard 510, refers all the time to ASME Section 5, Article 4, 5, and 3. EWS, probably some of you don't know what is EWS. It's American Welding Society, and it governs the building of carbon steel structures and bridge welding in the United States. And we have the equivalent in Canada, the CSA, as well with its W59. So these two also include phase array. Also, it's good to remember that it took some years to see these phase array sections added to those codes. Now, what about the FMC TFM? Actually, they asked me, currently is the only code in its section 5, article 4 in its 2019 release includes FMC TFM section. ISO code, as indicated in its website, will release a dedicated standard on February 2021. API 510 again refers to ASME code, so it could be, since it's working for phase array, it could be a window to use FMC TFM as well. EWS just released its D1.1 for 2020, so I don't think that FMC TFM is on the table right now. So if we focus on the ASME code, since it's the only one that includes FMC TFM, it has actually 3 main dedicated sections in its section 5, article 4. The first one is a mandatory appendix 11, full matrix capture. Second one is non-mandatory appendix F, which is examination of wells using full matrix capture. And the last one, specific personal requirement and training outlined in section 5, article 1. So in these dedicated sections, we can pick up some main requirements that we will discuss today. So a written procedure, of course, that talks about qualification and scan plan, the cal blocks, and this is actually different from the cal blocks of phase array. So we have a notch, a slot, this is the new stuff, and side drill holes, calibration that talks about amplitude fidelity, this is new as well, performance verification, this is also different from phase array. Personal qualification, the ASME code require 80 hours training with detailed content, and then we have examination, evaluation, documentation, etc. Actually, the main topics that will be discussed in the next sessions are underlined here. So scan plan, cal blocks, amplitude fidelity, performance verification, and personal qualification. So let's focus now on the scan plan, the probe selection as requirements from the ASME code. We will see in the next section as well some other requirements. But now, let's talk about the scan plan. The main steps to build a scan plan in TFM are the part and the well definition. So this is like phase array, the probe selection, same than phase array 2, the zone setting. Zone settings, this is something new compared to standard phase array where users have to select between sectorial scan, linear scan, or compound scan. Wave set selection, same thing. This is new. It's really specific to a TFM. Flow definition. Actually, flow definition is very important here, especially when we are using indirect mode or self-tandem mode. So we can have planar, spherical, and if planar, we can put the expected angle. Following these 5 steps, X3 will generate an acoustic affluence map or AIM. This is what we call modeling. And we will see that modeling is very important. And it is essential actually. So because that many wave sets are available, commonly more than 9. So when we talk about wave sets, we are talking about 2T, 3T, etc. A proper wave sets are critical for detection and sizing. So if we don't select the right wave sets, probably we won't have a good detection and of course a good sizing. The type, the orientation and position of the flow influence wave set selection as well. Part geometry will change wave set results. Focus is expected everywhere in the zone, but it needs to be confirmed by using the proper probes, frequencies, etc. So modeling is really a very essential tool when building a scan plan in TFM.
Dali, I'm going to interrupt just a second. Your cursor is not moving in case you're moving it around to point out things. I don't see your cursor moving. It's just sitting on the screen at the left side.
I will use it actually later when I have figures, etc. So it's not
okay.
Thank you, Greg.
Yep.
So let's see how this modeling can influence our scan plan. Here we have a 5L60 pipe wizard probe mounted on a wedge of N 60 in shear mode. So here we have our mode in pulse echo, and we are using TT. And our defect or our flow here is considered as spherical. We have our zone, we set our zone, and we have here a G bevel. Our sensitivity index here is 47.38. We have an index offset of -15. What if we change one of these parameters? Let's see what would happen. Here, we just changed the waveset, so from 2T to 4T. And we see that the coverage here is better, but the sensitivity index, so the general, let's say, sensitivity provided by the probe for 4T is less than the other case. Here we have 23.05. We kept, or we maintained the spherical here flow type. Now, we change from spherical to planar, as this is a G-type weld. As you can see, our sensitivity index dropped to 0.5, but also we have a very poor coverage of our area here. So we are covering only the top of the weld. The same thing, it was TT, so we compared TT in pulse echo mode just by changing the flow type. So this is why it's very important to know exactly what we are looking for. Is it for spherical flow or for planar? Here, if we have a G-type bevel like this one, so self-tandem mode would be better for covering especially the bevel, let's say, wall. So here we are using 3T in self-tandem mode. Of course, we are still using the same probe here. And we are looking for planar here defect or flows at -3 degrees. We can see that actually our zone is not well covered, even if we have a sensitivity index of 3.15, but the coverage of this sensitivity inside our zone is still very poor. So what to do in that case? Probably we need to change the probe. Let's see with another probe. Here, from the Pipe Wizard one, we move to the 5L64A32. So we kept the same parameters of waveset and flow type and direction, and we just changed the probe from 5L60 to 5L64. We have just 4 elements more than the other probe, but also we have a pitch that is different. So we moved from pitch of 1 millimeter to a pitch of 0.5 millimeter. We notice a better coverage and a better sensitivity index. This actually brings us to the next slide where we will compare 4 probes. Here we have 5L64A2, 5L64A32, 5L64A12, and 5L64 near wall 1. So we have the same number of elements and the same frequency. The only thing that changed here actually is the pitch, in addition, of course, to the wedge. And we can see clearly that for comparable pitch, we have the same coverage here in our zone. But when we change the pitch to 1 here for the near wall probe, we clearly see that most of the sensitivity or the coverage, the good coverage of sensitivity is just below the probe and not inside our zone. So here we understand clearly that the parameters of the probe are very important in the selection of the right one. So let's have a look on how the code talked about these parameters of the probe. What are the parameters to consider? First, we have the aperture. So larger it will be, longer will be the near field. Actually, I kept the definition as it is in the code, but I will explain it in my own words. For number elements, generally, higher numbers provide better resolution. For pitch and let's say element width, because they are very related. So small pitch, small element width, and the large number of elements provide a large optimized examination area. Wavelength or frequency, so higher frequency improves resolution, so this is proper to the probe, but also we have to consider the material velocity that impacts the wavelength. So when material velocity increases in the material, it will increase the wavelength. The type of application and the area of interest are factors that influence the selection of one probe or the other, of course. And any given probe that performs poorly with standard phase array will probably perform poorly with the FMC TFM as well. This is also mentioned in the code. Now we can move to the next section that deal with calibration. First of all, let's talk about amplitude fidelity. So this is the measurement in dB of the maximum amplitude variation of an indication caused by the TFM grid resolution. So here we are talking about a variation that is related to the TFM grid resolution. The parameters that influence the amplitude fidelity value are probe frequency and bandwidth, material velocity, grid resolution, the applied envelope, etc. When amplitude fidelity is above 2 dB, the user can either increase the resolution, reduce the zone size, or increase the probe frequency until the requirement is met. Here we are talking about 2 dB since the code mentioned that any inspection that is conducted shall have an amplitude fidelity less than 2 dB. Let's now see how amplitude fidelity vary in different axes. So we are using a 64-element probe at frequency of 7.5 megahertz. In contact, we don't have wedge. Velocity of the carbon steel block is 5,890 meter per second, of course. Resolution of 5 points per wavelength, and we will move the grid actually on the left, on the right, on the top, and on the bottom by 3 wavelengths by 100. And we will see how the amplitude fidelity will vary in the vertical, the horizontal, and the lateral axis. So as you can see here, we moved the grid a little bit. We are reading here the amplitude. It's like the full screen height actually reading that is provided on phase array machines. And we can see there is a slight variation that indicates that there is a little difference in dB when we move the grid on the left or on the right. Same thing for the vertical axis as well. And actually here we see that we have a 0.16 dB difference on the horizontal axis and 2.52 dB on the vertical axis. Now let's see for the lateral one. Here, the same thing. We see that there is a slight changes in the lateral axis. So we should be very careful when we talk about amplitude fidelity. It's not only moving or changing in the horizontal axis or in the vertical axis, but everywhere, actually in all directions that an ultrasound path could have. So here, well, there is one question: how the OmniScan X3 is displaying the amplitude fidelity, or the amplitude fidelity that is displayed in the OmniScan comes from which axis? So we are taking actually the worst measurement, or if you like, the lowest amplitude fidelity, which means the highest value. So OmniScan is showing you the worst case of amplitude fidelity in all these axes. Resolution effect on amplitude fidelity. Actually, this one was treated in other webinars as well. So I will go fast on this one. So as you can see, we are moving from a resolution of 5 points per wavelength to a 20 points per wavelength. And we see that amplitude fidelity is going from 5.2 dB to 0.3 dB actually, which is of course good to have. Even 1.2 still compliant with the code, of course. Now, another feature we have in the X3 is the envelope. So a TFM envelope is obtained by computing the norm of 2 different TFM images. One computed using the standard acquired FMC, and the second computed using the Hilbert transformed FMC. So this one, the figure on the left, is a portion of an acquired elementary A-scan, like it comes from the FMC acquisition. And here, actually, the black dots here are representing the new A-scan treated by the Hilbert transform. So here we are losing, of course, the negative phase, but we're not losing any signal. So for people who are sometimes discussing about will we lose a diffraction or a signal somewhere in our scan when we apply envelope, no at all. We don't lose any signal actually. We treat the signal. And here are the results actually as we see them in the OmniScan. So on the left, we have the scan, the end view actually of an indication without the envelope. On the right, we have it with the envelope. So here, of course, the envelope improved our ability to size if we are using an amplitude-based technique. It also improved the amplitude fidelity, but be careful here, we are talking about the same grid resolution, and also it may improve the acquisition rate, but also here we are talking about the same amplitude fidelity. Here, let's see a demonstration. Actually, I took these results from a white paper done by my colleagues here in Olympus. And you can find this paper actually by visiting our website, going in resource and looking for white papers, and you will find an article called Use of the Total Focusing Method with Envelope Feature. So the experience or the test that they did consisted of using the OmniScan X3, a probe of 5L32A31, a wedge of SA31 and 55S, a steel block with a 1 millimeter diameter side drilled hole, a zone size of 20 millimeter times 20. So the zone that we are talking about is the yellow one here. And the red box is actually the zoomed area that we will use in the next slide. And we used a wave set of TT. To understand the next slide, I wanted just to have some, let's say, explanation. So on the top here, we will see a reading of amplitude fidelity and also the acquisition rate. When it's green, that means it's compliant with the code. When it's red, that means it's higher than 2 dB. This is the top picture will be the standard TFM. The bottom one will be the TFM with envelope. And we have the reading of grid resolution here noted in terms of wavelength fraction. So let's start with this one. We have an amplitude fidelity of 1.41 here, an acquisition rate of 46, and we are using a resolution of 9.3 points per wavelength. Applying the envelope here would ameliorate or improve the amplitude fidelity value here to 0.37 dB. Of course, the acquisition rate will be reduced. Here we have 1.85 dB as amplitude fidelity. We apply the envelope, it became 0.48 dB as well. Again, here the acquisition rate will drop a little bit. And of course, we are maintaining the same here grid resolution. For this case, we have an amplitude fidelity of 3.63 dB, and we have an acquisition rate of 93.2. So this is a good case, actually, where our setup is not complying with the code. So by applying the envelope, amplitude fidelity became 0.88, which is complying with the code. Of course, we are losing some speed of scan here. This is for resolution of 5.9 points per lambda. We have another example with an amplitude fidelity that is not complying with the code. Here we have 8.58. We have a resolution of 4 points per lambda. And as you can see, we apply the envelope, and the acquisition rate, of course, drops, but the most important parameter here is the amplitude fidelity, which became 1.77 dB. So in conclusion, for the same resolution, if you have an amplitude fidelity higher than 2 dB, by applying the envelope, you can reduce this value and become code compliant. Here, because we are discussing about the acquisition rate as well, I wanted to show you that for very comparable amplitude fidelity values. So here we have two pictures with no envelope. The first one is at 1.85 dB. The second one is at 1.41 dB with a resolution of 9.3 points per wavelength here and with 8.1 there. So if we apply the envelope, we will have one, or we can compare actually the amplitude fidelity but because they are very comparable. But by applying the envelope, we can reach an acquisition rate of 79.6 compared to 57.9 here and 46.8 here. So the conclusion here to make is that for comparable amplitude fidelity values, or without changing the amplitude fidelity, by applying the envelope, we can increase our acquisition rate. Now let's see another stuff related to the amplitude fidelity. Multi-group. Many people are asking about multi-group. If we do a multi-group, can we continue to consider that we are code compliant or no? So it depends, of course, but we can have some answers in the next slide. So in the code, in appendix F461, it says the amplitude fidelity check shall be performed for each path mode that will be used during the inspection. So this is the most important phrase that I will take. Therefore, for all groups of a given setup, we need to check the amplitude fidelity. Using the OmniScan X3 flow detector, it's possible to configure and run a code compliant inspection using up to 4 groups. So if you are using 3 groups or 4 groups, a resolution of up to 1024 times 1024 per group will be reached. An amplitude fidelity below 2 dB also can be granted for each group. So no problem, you can work on multi-group and being code compliant. We can have a test also or a demonstration for this one. So we have a part of 24.4 millimeter in carbon steel with a weld preparation as V bevel. We have 2 flows, an OmniScan, a probe 5L64A32, a wedge of N55S. So the 2 flows here are a lack of fusion and a crack on the other side of the weld, the center line. Of course, we should start with a scan plan. As I said, scan plan with the aim is the first step to be code compliant. So here we can try the 2T, 4T, 3T, and 5T. So we are using 4 groups. This is the result that we obtained, and we are looking for the first actually defect, which is the root crack. So here we see that 3 groups detected perfectly this defect. So we have the 2T, the 3T, and the 5T. However, for the 4T, we are missing this defect, or we see a little signal here. Actually, in the OmniScan, you can recognize your main end view here on the screen just by having a look on the green dot we have here that is corresponding to the green dot that is here. So here we are looking to the 5T. Actually, I selected the 5T just to see how straight is the indication. So it corresponds to the orientation of a crack. If we go to the next slide, so as we said, we detected with the 2T, with the 3T, with the 5T, and actually a very slight indication here in the 4T. The difference actually between the 2T and 3T or 5T here is the orientation. So 2T is like standard phase array. So the orientation of the indication here is not straight as the root crack should be, but with 3T we have a better imaging of that crack. Let's have a look on the second now defect or second flow, which was a lack of fusion. So we clearly see that only one group here detected well this type of flow. So it's the 4T, and it's normal since it's like standard phase array. This is the best way or the best route actually to detect such flow orientation. So here for 2T, 5T, we see nothing, a little noise, but nothing really important. In 3T, we still see some indication, but we will see it here. Actually, that there is an offset between the real position of lack of fusion and the position shown on the 3T. So here the 4T is showing us the best, let's say, view. For all these groups, so we use it for 2T, 3T, 4T, and 5T. We have the same zone, of course, here, and we obtained the same amplitude fidelity, 1.9 here. Actually, it could be improved even, but it was perfect as it is right now. So 1.9 as a value for amplitude fidelity, and for resolution, also the same for all the 4 groups. So multi-groups won't affect your code compliancy if you do well the, let's say, the zone selection, if you select the right wave modes for your detection and sizing, etc. Of course, multi-group will improve your inspection, not to the contrary. Now let's talk about something that is trending actually on the social media, double thickness. So some users with phase array experience and phase array, let's say, background may use one group in TT mode and set the thickness to 2 times its value. So they are creating something similar to phase array inspection. The plus of such methods would be flow detection and imaging will be very similar to phase array. Only one calibration is required as well. However, this is not recommended if self-tandem modes are needed. And we will see that in the code, probably, those self-tandem modes or those indirect modes will be needed. Not optimal for thick component as well, because when you double the thickness, there is a limit for the zone size that won't affect your amplitude fidelity. We will discuss that actually later. So let's see the results of a test that we did on a part of 15.875 millimeter in carbon steel as well, with a weld preparation of X bevel. 2 flows again here, and using the OmniScan, the same probe, 5L32A32, and an N55 shear wedge. So as I said, we have 2 flows here. We have a lack of fusion here, and we have a root lack of penetration in this one. So, of course, we start with aim. We will have 2 T groups, and here I wanted to show you the importance again of the orientation of a flow. So we are using a sample thickness in the second also image, but the difference here is the spherical or planar orientation of the flow. So here we have a spherical one. Here we have a planar at plus 30 degrees. As you can see here, the coverage is completely different. So the interaction between the ultrasound here and here with the flow is completely different. So it's very important again to have a knowledge about what you are looking for as flow. Here, also another example of 4T, using 4T mode with a planar, let's say, flow at minus 30 degrees. We see also another or a different coverage here, and a 2T with doubling the thickness. So this is what we intend to do, to compare between the different modes and to compare also with the doubling thickness, let's say, technique. And here we considered that the defects are spherical just to see the coverage of the, let's say, ultrasound map. Now let's have a look on results. So we have 2 groups here. We are looking at side views of 2 groups, 2T and 4T. If we look at the 2T one, we are detecting only one flow. For 4T1, same thing, we are detecting only one flow. So here, again, the green dot, like tell me where, which one I'm looking to. So I'm looking to 2T here, and as you can see, at the position of the first flow, we have nothing in the 2T mode. But if I move my data cursor on the second flow, I clearly see that the lack of root penetration is detected by the 2T, but nothing here in the side view of the 4T. Next one, we are focusing now on the 4T here. So first defect was detected by the 4T as expected, actually, since it's a lack of fusion. But for the next one, we see nothing in the 4T group and nothing, of course, in the end view. Now, what about the group that we use a double thickness for it? So it's 2T, but we have double the thickness. This is why we see like the double V layout of the weld flipped again here. So it's like phase array exactly, like standard phase array. So for the first defect here, we can see it clearly. It's well detected, but it's flipped, of course. And the second one also is detected. So here, actually, before I explain the stuff regarding the amplitude fidelity and the zone, so the conclusion, if we are using double thickness with 2T, for sure, we will detect both indications just by one scan. The same thing, if we are using TT and 4T, we will detect both indications. However, each group will detect one of them. So it's up to the user actually at this point. However, can we check the amplitude fidelity and resolution for each one just to be sure that we were code compliant? So here we have 0.7 dB when using the TT with doubling the thickness, so it's okay. And this one also, we have 0.7 dB for both groups. So each group has 0.7 dB as amplitude fidelity, same resolution here, nothing changed actually. Even if we are doubling the zone here, actually the only thing that changed is the number of points in the grid. And in the OmniScan X3, this is a really fantastic thing. So as long as you are between 64 points and 1024 points per grid, we are still okay. So even if you double the zone, but you are still inside this, let's say, range, you are still okay. So nothing would change, not the amplitude fidelity, not the resolution. So, but suppose that you are inspecting 100 millimeter part, doubling the zone would mean 200 millimeter. So probably this is higher than the capacity to cover, let's say, or higher than the capacity of covering this area by 1024 points. So this may affect the amplitude fidelity. But again, the X3 will allow you actually to do such manipulation or such technique easily, since the amplitude fidelity and the resolution will be perfectly code compliant. Now let's move to another actually topic, which is the general calibration requirements. So here I put just the phase array ones as a comparison, not to really to go through, or just to have an idea how it changed from phase array to FMC TFM. So here actually the blue ones, since they are part of performance verification, this is the ones that we will discuss in the next sections. But just to have an idea, so we have a contact wedge verification, system delay and velocity verification, and performance verification that includes resolution verification, path verification, and sizing verification. And as in phase array, the code put or input the DAC inside the general calibration requirement. So here I just put the sensitivity apart because it's not included in this paragraph, but I put it just to have the same comparison with phase array. First of all, let's have a look on the calibration block dedicated for TFM. So it has to include a slot to make the path verification, SDH to do resolution verification and sensitivity calibration. Of course, here the placement of SDH is not really correct, so it's just a representation. Length and height and sizing verification, in other words, should be done using top notch and bottom notch, or sometimes just top notch and you flip the block and you do it on the other side. The thickness here of the cal block, and we will talk about it later because this is a very important parameter to discuss. For piping, the code requires a thickness that is plus or minus 25% of the thickness of the part, and non-piping 90%, between 90% and 100% T, so the thickness shouldn't be other than this range. As I said, we will discuss about the thickness in the next section. Let's start first with performance verification, and we will go through step by step. So, or actually, we will see all of them in separate slides. And actually, here it's a courtesy of Shane Walton from University of Ultrasonics. So thank you very much, Shane, for sharing with us this content. As long as you see actually this mention of courtesy, so you will know that Shane Walton provided us photos and data. So thanks again, Shane. So here, Shane used an Omniscan X-ray with a probe of 5L32A32 and a wedge N55S. And of course, this is where we put the probe to make our resolution verification. He used 2T and 4T, and as you can see, we are perfectly resolved. Here, you can ask why we are not using the 3T and the 5T. 3T and 5T won't really display a perfect image of these two surgery holes, and this is subject to discussion too, because 3T and 5T are not really dedicated to detect such indication. Second, performance verification. This is completely new in the code, and this is dedicated really for TFM, and it's subject to discussion as well from many people. So using pulse echo modes cannot detect the full extent of the slot. This is why some people are discussing or arguing of the use of this slot. Therefore, self-tandem modes or indirect modes are necessary. Multi-group in Omniscan X3 unit actually will allow you to do such verification just by one pass. So you don't need to make four different setups to make it happen. As you can see, if we were using 2T and 4T only, we won't be able to see the full extent of this slot. So 3T and 5T are necessary to do so. And here there is an important point. So in the code, they say the imaging paths used during calibration shall be the same as those for the examination. So here, that means that if you are using 4 groups during calibration for path verification, for example, so the examination should be done using the 4 groups. Imagine if you don't have 4 groups in your machine and you want to do the inspection. So if you have just one group, you have to run 4 times the scan or the weld, because to prove that you detect the full extent of the slot, you use it 4 runs as well. So this is very important. The next performance verification is the length sizing verification. So it's used on the notch here. Of course, you can, if you have just one notch, you have just to flip your cal block. And here, actually, the measure was almost 1 inch, and it corresponds actually to the length of the block provided by Shane. The height sizing, it's used also on the same notch. So here we see the 4 groups. For 2T and 4T, the sizing will be similar to phase array. So you see the tip diffraction here, and you put on the maximum, and you find almost the right height. Actually here, it's 0.074 inch. For 3T and 5T, it's different. So you can do the 6 dB drop. So you should look for your maximum and then put your cursor on the first drop to 6 dB, and then you find the value you are looking for. Last thing to do is the sensitivity. Here again, we are using only 2T and 4T. For 3T and 5T, I recommend, and this is my personal view as a former inspector before, I would use notches to set my sensitivity on them. So regarding the cal block thickness. So the most important information, you can find it in figure 11.434.1-1 calibration block, just under the figure. So it says block thickness for piping shall be plus or minus 25% T. Block thickness shall be no less than 90% and no more than 120% of the average weld thickness T. When 2 or more base material thicknesses are involved, the calibration block thickness T shall be determined by the average thickness of the weld. This is a little problematic, actually, because self-tandem modes results are very sensitive to a part's thickness and geometry. An error in the time of flight calculation could lead to poor detection capability. So if you are using a different thickness for the calibration block, be very, very careful, especially with the indirect mode. So we are talking about 3T, 5T, etc., TLT. So be very careful. And to demonstrate this issue, actually, we used a 5L32A32 Pro positioned on a 19 millimeter block with 2.5 millimeter SDH located at half depth. And we will compare actually results with 2T, 4T, and 3T modes while varying part thickness by plus or minus 25%. This is for 2T. As you can see here, the position of the indication actually changes. This is like phase array exactly. So 2T, no problem. We don't lose detection, but of course we lose accuracy on the position. 4T, this is more problematic actually. So here with 19 millimeter, this is the perfect actually location of the side drill hole. 15.6 minus 25% than the real 19 millimeter real location, and we can see that position changes. However, when we add 25%, so 23.75, we can see wrong position, but also another indication here, and this is also, we can understand that as it's 4T, so we are doubling the signal. Now for the 3T, and this is the most problematic point. So 19 mm, we see that it's perfect. The location of the indication is good. Now we just removed or changed the thickness to 15.6, and we see that we have many indications actually, not only two main indications, but we still have some indication here and noise. So let's see another one, 23.75 millimeters. As you can see now, we have even some indications just before the main indication, and we cannot really rely on that to say that this is our indication. So be very careful when using self-tandem mode or indirect mode like 3T and 5T. If ever you have just the same thickness or one thickness for the calibration block and you need to inspect a different part thickness. So my recommendation is to use the same calibration block thickness than your part to inspect. Another actually demonstration, this time not on a side drill hole, but on a notch. So we have a notch at 21.6 millimeter, and we changed the thickness like 2 times here to 24 and to 26.89. And as you can see, for the right depth of thickness, or the right depth of the notch, sorry, we have a very good signal. We changed the thickness and we lost a lot of amplitude here. And here, actually, we are almost about to lose our detection at all. So again, be very, very careful when using the self-tandem modes, especially when you don't have the right thickness for the calibration block. So now we will move to the most important parameter in any inspection, which is the personal. Just to have an idea about the requirements of some certification bodies for phase array, I put examples of PCM and CSWIP, API, the QEPA certification, and ASNT as well. So, of course, if you are starting as a level 1, you would need more hours than level 2. And actually, here, I just wanted to give you an overview of what you need exactly to be a phase array inspector compared to what you need for a TFM here, as mentioned in the ASME code. So the ASME code says it should be 2 weeks or 80 hours, and it should cover 14 main topics actually, and it went in detail. So from overviews of, let's say, the general phase array and duty basics, then the basics of TFM, etc. And of course, one of the most important things is the hands-on. And as you can see here, actually, the X3 has some features that are proper to Olympus and proper to the brand. So if you are used to work with the X3, it's better to continue and do your training with the X3 as it respects the code perfectly, for example, with the multi-group, with the envelope feature, with the amplitude display, with the amplitude fidelity display, etc. So now one part that is probably funny, myths and facts. So because in social media, actually, there are a lot of facts that are discussed and a lot of myths also that are spread and taken as true. So some of them, I just pick up 3 here. So according to the code, weld inspections required a TCG setup. Absolutely wrong. So in TFM, for TFM, the ASME code doesn't mention a TCG setup at all for such inspection. According to the code again, A-scan data are required. So this is wrong as well. So we don't need the FMC data and the A-scan raw data for TFM inspection. The last one actually is envelope is equivalent to a low pass filter. This is absolutely wrong too. So we cannot compare envelope with a low pass filter at all. And if you have questions on that one, you can send me an email and I would be pleased actually to go in details for that with you. Some facts now. So it is code compliant to have amplitude fidelity calculated. So you use the theory to calculate the amplitude fidelity rather than experimental validation. This is absolutely true. Prior to examination, resolution, path, and sizing verifications must be conducted as a part of the calibration process. Absolutely, this is new thing in the code, and it's a part of calibration actually. According to the code, it's not mandatory to collect FMC raw data, so we just answered on that question, and this is absolutely true. Now, let's have a summary, and let's actually have the conclusion of this webinar. So, FMC TFM is governed by the same laws of physics as phase array. However, the technique requires additional training since it involves new concepts and new parameters. In comparison with requirements for phase array inspection, amplitude fidelity is a new essential parameter to consider according to the code. A successful inspection is based on the selection of the proper probe and the right wave modes. AIM, so the acoustic influence map, multigroup, and the TFM envelope are essential tools for scan plan building, for the calibration, and for the sizing, and for being code compliant. So thank you for your attention. Sorry if I was somehow long, and I give you the parole, dear Greg.
Thanks, Dali. On behalf of Olympus, I'd like to thank all the attendees for joining us, and Dali for his participation and expertise in today's event. We hope this material presented was informative and useful. This webinar will be archived on our website at www.olympus-ims.com. As I said before, everyone today who registered for the event will receive a follow-up email with links to the archive presentation, whether you attended or not. So we hope it was informative and useful, and that's going to do it for today. Thank you again for your interest in taking the time to attend this Olympus event. We will see you again next time.